Welcome back to QHSE Talks. You know, usually when we talk about workplace hazard, there's this expectation of visibility.
Right, yeah, you expect to see it.
Exactly. If you walk onto a factory floor or a construction site, the dangers usually just announce themselves, you know. You see a spinning saw blade without a guard, or maybe a chemical spill pooling on the concrete.
Or a worker leaning over an exposed ledge. It's obvious.
Yeah, the safety inspector can just point a finger and say, right there, that's the danger. Fix it. It is incredibly objective, safe or not safe.
Mm-hmm.
We really like our hazards to be tangible physical objects that we can, well, put a solid yellow barrier around. But then you step into the world of industrial acoustics and occupational noise exposure, and suddenly that visual inspection is, it's entirely useless.
It really is. It's the absolute definition of a pervasive, invisible threat.
Right, because you are walking into a hazard landscape that is completely invisible. And honestly, without the right mathematical tools to decode it, it feels like trying to navigate a minefield in the dark.
Yeah, because sound waves don't leave physical bruises that you can just, see right away at the end of a shift.
Mm-hmm.
When an employee is struck by a falling object, the injury is immediate. It's visible.
Yeah, someone's bleeding or they have a broken bone.
Right. But the damage inflicted by acoustic energy happens on this microscopic scale, deep inside the inner ear. It is permanent, it is cumulative, and by the time the worker actually notices the biological deficit, well, the damage was done years, maybe even decades ago.
Wow.
Yeah, it's a silent epidemic of hearing loss, which is ironic, given that it's caused by noise.
Yeah, that is ironic. And that invisibility is exactly why this edition of QHSE Talks is a comprehensive deep dive into the source material for ASP Domain 1, Topic 5.
Right, calculating noise hazards.
Exactly. Whether you are a safety professional actively prepping for your associate safety professional exam, an industrial hygienist trying to refine your field skills, or, just someone who wants to fundamentally understand the invisible forces battering your eardrums daily, consider this your ultimate guide.
And we really do have a lot to cover today.
We do. We've gathered some incredibly dense, highly technical source material today. We are looking directly at the Bowen EHS CSP exam practice problems, the My Safety Prep Exam Study Guide, and the Safety Professionals Reference and Study Guide by W. David Yates.
Which are fantastic resources.
Oh, absolutely. These texts are essentially the toolkits for decoding the math of going deaf.
And the calculations outlined in these texts, they aren't just academic exercises meant to torture exam candidates.
No, it definitely feels like that sometimes.
I know. But they form the absolute bedrock of modern occupational hearing conservation. If you cannot calculate the hazard, you cannot mitigate it.
Right.
And the math here is notoriously tricky because it doesn't behave the way our brains intuitively expect numbers to behave.
Yeah, and I want to make a promise to you, the listener, right up front. Our mission today is not to just read a list of sterile formulas aloud.
No, nobody wants to listen to that.
That is terrible audio, and worse, it doesn't actually teach you anything. We're going to dig into the actual physics and the regulatory logic, the philosophy, really behind noise exposure.
We're going to explore everything from time-weighted averages to the wildly counterintuitive math of dual machinery.
All the way down to why the foam earplugs you buy at the hardware store might actually be lying to you about their noise reduction ratings. Okay, let's unpack this. If we are going to understand how sound damages the human body, we need to know the official speed limit. What is the baseline rule of the game here?
Right. So the baseline rule is dictated by the Occupational Safety and Health Administration, or OSHA.
The big boss.
The big boss. The primary number, the anchor point that you will see at the very top of the My Safety Prep Guide is OSHA's permissible exposure limit, known as the PEO.
And what is that limit exactly?
For occupational noise, that limit is set at 90 dBA averaged over an 8-hour workday.
Okay, 90 dBA for 8 hours.
So.
And the sources are careful to distinguish between different types of noise before we even start the math, right?
Yes. They define continuous noise as a sound that is constant and ongoing without any breaks.
Like, imagine a heavy industrial ventilation fan or a massive continuously running conveyor belt. It just hums or roars without stopping.
Exactly. And they contrast that with intermittent noise, which is composed of sounds that stop and start like a pneumatic press stamping metal every few seconds, or maybe a forklift driving by periodically.
Got it.
That distinction is vital for how industrial hygienists actually go about field monitoring. But regardless of how the noise is generated continuous or intermittent, that 90 dBA threshold for an 8-hour shift is the universal regulatory anchor.
So if an employee is exposed to exactly 90 dBA of noise, they can legally work for exactly 8 hours without exceeding the permissible limit.
Precisely.
But let's look at the table provided in the Yates reference guide, because this is where the math immediately gets incredibly aggressive. The OSHA standard operates on what is known as a 5 dB exchange rate.
Yes, the 5 dB rule.
Let me explain what that actually means in practice for the listener. We established that 90 dBA allows you 8 hours of exposure. If the noise in that room goes up by just 5 decibels, hitting 95 dBA, your permissible work time doesn't drop by an hour or two.
No, it is cut exactly in half. You only get 4 hours.
That is the crux of the regulation, isn't it? It is a strict halving rate.
It absolutely is.
And it doesn't stop there. If the noise hits 100 dBA, you are slashed in half again, down to 2 hours. At 105 dBA, you only have 1 hour of permissible exposure.
At 110 dBA, you get half an hour. Just 30 minutes.
I need to pause here because this makes no intuitive sense to me. If I add just 5 decibels to my environment, I lose half my entire workday.
Yeah, half is gone.
Why in the world isn't this a linear scale? I mean, if the volume goes up slightly, shouldn't the time go down slightly? It's like an aggressively steep tax bracket for your ears.
It feels aggressive because human beings naturally think in linear terms, like inches on a ruler or pounds on a scale.
Right, like if I add 5 pounds to a 50-pound weight, it's just 10% heavier.
Exactly. But decibels are not a linear measurement of distance or weight. They are a logarithmic expression of physical pressure and acoustic energy.
When you say logarithmic, you're talking about powers of 10, right? Like compressing massive numbers into smaller, manageable chunks.
You've got it. Let's look at the raw physics of sound waves for a moment. Sound is just mechanical energy creating invisible waves of high and low pressure in the air.
Okay.
Our eardrums, the tympanic membranes, detect these microscopic pressure changes. Now, if we measured sound pressure using a standard linear scale like Pascal's, the numbers would be absurdly huge.
How huge are we talking?
Well, the difference between the quietest whisper a human can hear and the roar of a jet engine is a factor of millions, if not billions, of units of pressure.
Oh, wow. So if a safety inspector had to write down the linear pressure, they'd be writing numbers with a dozen zeros on their clipboard.
Precisely. It would be an administrative nightmare. So scientists created the decibel scale to compress those massive physical pressure differences into a tidy numerical scale from roughly 0 to 140.
Makes sense.
But because it's heavily compressed, a very tiny numerical increase on the decibel scale actually represents a massive exponential increase in raw physical acoustic energy hitting the ear.
Okay, let's quantify that massive increase because that's the part that really matters here. How much does the physical energy actually go up if I raise the volume by just a few decibels?
This is where the physics gets fascinating. If the sound level goes up by just 3 decibels, the actual physical acoustic energy in the wave literally doubles.
Wait, really? 100% increase in destructive energy is represented by just the number 3?
Yes, exactly.
Hold on. If the physical energy doubling is represented by 3 decibels, then why does OSHA use a 5 decibel exchange rate for cutting the worker's time in half? Shouldn't the time be cut in half every time the energy doubles?
You've just hit on one of the most significant historical and regulatory debates in the entire field of occupational health.
Really?
Yes. Strictly speaking, from a standpoint of pure biological physics, you are absolutely correct. If the destructive energy doubles, the safe exposure time should theoretically be cut in half.
Right. And in fact, the National Institute for Occupational Safety and Health, NIHL, along with the Department of Defense, the EPA, and many European regulatory bodies, they advocate for and utilize a strict 3 decibel exchange rate.
So NIHL says if you hit 93 decibels, you only get 4 hours. But OSHA, the actual federal enforcement agency, says you can go all the way to 95 decibels before they cut your time to 4 hours. Why the discrepancy? Why is OSHA being more lenient than the actual physics suggest?
It comes down to a deeply debated physiological theory combined with regulatory compromise. Decades ago, when OSHA was formulating these enforceable standards, industry representatives and some acoustical scientists argued that occupational noise isn't usually a constant, unbroken drone.
Right, it fluctuates. Workers go to the bathroom, they step into a quiet hallway, the machines cycle down.
That intermittent noise we defined earlier.
Oh, exactly.
The theory proposed was that during those brief periods of relative quiet, the microscopic hair cells in the inner ear, the spheriocilia, are given a chance to briefly rest and physically recover from the acoustic battering.
So OSHA adopted the 5 dB exchange rate as a way to mathematically account for these supposed biological periods of recovery in a dynamic workday. It was also, frankly, a massive practical compromise to make the regulations economically feasible for the manufacturing industry at the time.
Wow. So NIHL relies strictly on the math of the energy, while OSHA tries to factor in a controversial biological recovery period. But regardless of the debate, if you're taking the ASP or CSP exam, or if you're writing a legal compliance report for your factory, OSHA's 5 dB rule is the law of the land.
It is the enforceable standard.
Yep.
You must calculate permissible time based on the halving of hours for every 5 decibel increase.
Okay, so 90 decibels is the baseline for 8 hours. And if you have a single employee whose entire job is to stand perfectly still next to a single machine emitting a constant drone all day, calculating their hazard is easy.
Very easy.
You look at the table. Are they at 95 dBB? Yes. Did they work more than 4 hours? Yes. Boom, violation. But real life is almost never that static. Workers are dynamic. Let's imagine a fabrication shop. You have a worker. Let's call him David. David spends his first 2 hours grinding metal, which is deafening. Then he spends 3 hours in a relatively quiet control room checking schematics. Then he spends the last part of his shift working near a loud pneumatic compressor.
A very typical day.
Right. How in the world do we calculate if David is safe at the end of the day when his exposure is constantly riding up and down the decibel scale?
That reality is exactly why we cannot just use the basic table. We have to utilize the concept of the noise budget, which the source texts officially refer to as noise dosage.
Noise dosage, which is usually represented by the capital letter D. The My Safety Prep Guide defines this dosage as the total amount of noise an individual is exposed to over a measured period, and it is always expressed as a percentage.
Right.
This percentage is the ultimate biological scorecard because 100% means you have exactly reached the absolute maximum legal limit for the day.
Yes, if you finished your shift at 99%, you are legally compliant. If you hit 101%, you are over the line and the employer is in violation. And to calculate this daily percentage, we use a specific summation formula.
What's the formula?
The formula states that dosage, or D, equals 100 multiplied by the sum of C divided by T.
Okay, let's strip away the algebra and look at what those letters actually represent in the real world. C stands for the actual duration of exposure at a specific noise level. It is the time the worker actually spent standing in the noise.
Yes.
And T is the maximum permissible exposure time allowed at that specific noise level based on that 5 dB halving rule we just debated.
To conceptualize it simply, C is the time you actually spent, and T is the time you were allowed to spend. When you divide the actual time by the allowed time, you are finding out exactly what fraction of your daily allowance was consumed by that specific task.
Right. You know, I think a biological metaphor works best here rather than thinking of it like a financial bank account.
I'd love to hear it.
Inside your inner ear, you have thousands of microscopic hair cells called stereocilia. They stand upright, kind of like blades of grass on a lawn. When sound waves enter your ear, they act like a foot stepping on that grass.
That's a great visual.
Right. So a quiet sound is like a child in sneakers walking across the lawn. The grass bends, but it springs right back up. A loud 100 decibel sound is like a heavy work boot stomping on the grass.
Oh, yeah.
Every time you expose yourself to a loud noise, you are bending those blades of grass down. The percentage of your noise dose is essentially measuring how close that grass is to snapping off permanently. Once you hit 100%, you've pushed those microscopic structures to the absolute brink of permanent biological failure.
That is an incredibly accurate physiological analogy. The calculation is determining exactly how much cumulative stress you've placed on those hair cells across various different environments.
But before we can add up all the stress, we need to know exactly how much time is permitted at any given volume. And sometimes the noise level doesn't land perfectly on OSHA's neat 5 dB table.
No, it rarely does in the field.
What if the noise is 97 decibels? The table jumps from 95 to 100. To find T, the permitted time for any random decibel level, the texts provide a secondary formula.
Yes, and this is where a scientific calculator becomes mandatory for the safety professional. To find T, you take the number 8 and you divide it by 2 raised to a specific power.
Okay.
That power is calculated by taking the measured noise level, subtracting 90, and then dividing the result by 5.
Let me put that in sequence so I can follow. Take the noise level, say 97, subtract the 90 baseline. That leaves 7. Divide that by OSHA's 5 dB exchange rate. That gives you 1.4. You then take the number 2 and raise it to the power of 1.4. Finally, you take the 8-hour workday and divide it by whatever that result is.
Exactly.
I know hearing that formula spoken aloud is like trying to mentally juggle sand, but conceptually, what is that formula actually doing?
Conceptually, it is simply a mathematical compressor.
Yeah.
It is taking the rigid rule, cut the time in half for every 5 decibels, and creating a smooth sliding scale.
Ah, I see.
It allows you to find the exact allowed biological limit down to the minute for any obscure noise level you encounter in the field, whether it's 91 decibels or 104.2 decibels.
Let's ground this entirely in a real-world scenario. The My Safety Prep Guide offers a great illustrative example. Let's look at a worker's specific shift. We'll track their exposure and calculate their total cumulative noise dosage at the end of the day.
Sounds good.
Here is the scenario. Our worker spends the first part of their day exposed to 95 decibels for exactly 3 hours. Then a machine breaks down, they move to a new area, and they are exposed to an incredibly loud 105 decibels for 2 hours. After that, they go home. We need to find out how much of their biological lawn they crushed today.
Right. The procedure requires us to look at each task in isolation, calculate the fraction of the daily limit consumed by that task, and then sum them together.
So task 1, we need to find T, the allowed time, for 95 decibels. We could run the complex formula, but 95 is squarely on the OSHA table.
It is.
90 decibels gets you 8 hours. Adding 5 decibels cuts it in half. So T for 95 decibels is exactly 4 hours.
Correct. Now we move to task 2. The 105 decibel exposure. Again, this is on the table, so we can count it down.
Let's do it.
90 dB is 8 hours, 95 dB is 4 hours, 100 dB is 2 hours, 105 dB is 1 hour. So the maximum permissible time, or T, for 105 decibels is just 1 hour.
Next, we divide the actual time C by the allowed time T to find our fractions. For task 1, they actually spent 3 hours in the noise, but they were only allowed 4. We divide 3 by 4, that gives us 0.75.
Right.
They consumed 75% of their legal limit before lunch. For task 2, they actually spent 2 hours in the 105 decibel noise, but we just established the absolute limit for that volume is 1 hour, so we divide the actual 2 by the allowed 1. That gives us 2.
Now we execute the summation step. We add the results of those individual tasks together to find the cumulative impact. 0.75 from the first task plus 2 from the second task equals 2.75.
And to turn that into our final dosage percentage, we just multiply by 100. 2.75 times 100 is 275%. That is the worker's daily noise dose.
What's fascinating here is what that number actually represents.
Right, let's connect that back to the biological metaphor. You were given a patch of pristine grass, 100% capacity. In the morning, you stomped down 75% of it. In the afternoon, the noise was so violent, the boots were so heavy, that you didn't just stomp the remaining grass. You theoretically stomped an area twice the size of your entire lawn.
It is a profound level of overexposure. When an industrial hygienist reads a dosimeter report that says 275%, they aren't just logging a minor infraction.
Yeah.
Hitting 275% means the worker's exposure is almost 3 times the absolute legal maximum established by federal law.
That's insane.
It indicates a total systemic failure of environmental and administrative controls in that facility.
If you are the safety manager, what is your immediate reaction to that number?
Immediate mandatory intervention. You cannot legally or ethically allow that worker to return to that specific environment the next morning without severe mitigation in place.
So what do?
You either have to fundamentally change the machinery, mandate highly specialized protective equipment, or completely restructure their daily schedule to pull them out of that environment.
The percentage really paints a terrifying picture of the biological toll. But here is the massive disconnect in the industry. A percentage is a great metric for a doctor or an OSHA compliance officer, but it is practically useless for a mechanical engineer or a procurement officer.
Yes, that is a huge problem.
If I'm a facility manager and my worker comes in with a 275% dose, I know I need to fix the room. I go to an engineering catalog to buy sound dampening acoustic panels or maybe a quieter replacement motor. But those catalogs don't sell percentage reducers.
No, they certainly don't.
They don't rate their equipment by how much dose it prevents. They rate everything in decibels. So handing an engineer a dosimeter report that says 275% gives them no actionable data to design a structural solution.
Exactly. The dose percentage isolates the cumulative biological reality. But structural engineering and facility design speak the language of sound pressure levels, decibels.
We have to bridge that gap.
We do. We have to take that messy, fluctuating day of 3 hours here and 2 hours there and translate that 275% dose into a single recognizable decibel number.
And that translation process is what the sources refer to as calculating the TWA, the time-weighted average. It's essentially a theoretical smoothing out of the day. It asks the question, what single continuous unbroken decibel level playing for a full 8 hours would have caused this exact same 275% damage?
And this conversion from a percentage dose back into an equivalent decibel level relies on a specific formula provided in the Yates reference guide.
I am looking at this formula, and it is a beast. For anyone taking the ASP or CSP, you absolutely have to internalize this.
It's critical.
The formula states TWA equals 16.61 multiplied by the base 10 logarithm of the dose divided by 100, and then you add 90 to that entire result.
It sounds intimidating, but it breaks down logically.
Let me say that again to let the shape of it sink in. You take your percentage dose, divide by 100, you take the base 10 log of that number, multiply by the constant 16.61, then add the 90 baseline. Let's run our 275% dose through this conceptual machine to see what pops out for the engineers.
Let's break it down systematically. Our dose, D, is 275. Step 1 is inside the parentheses. We divide D by 100. So 275 divided by 100 gives us 2.75.
Now we hit the logarithm. We have to take the base 10 log of 2.75. For those who haven't wrestled with logarithms since high school, the base 10 log is essentially asking a specific question. 10 raised to what power equals 2.75?
Right.
Since 10 to the power of 0 is 1 and 10 to the power of 1 is 10, our target number of 2.75 sits between 1 and 10. That means our answer has to be a decimal somewhere between 0 and 1. If you plug the log 10 of 2.75 into your scientific calculator, it spits out roughly 0.4393.
The logarithm acts as a mathematical compressor, taking wide variations in dosage and squeezing them down. Next, according to the formula, we take that logarithm result and multiply it by a very specific constant, 16.61.
Wait, I have to ask about that number. 16.61 seems incredibly arbitrary. Where does it come from? Did OSHA just pull it out of thin air?
Not at all. It is directly mathematically derived from OSHA's 5 dB exchange rate. It is the numerical linchpin that allows the formula to translate the logarithmic compression back into the specific scale OSHA regulates.
Really?
Yes. If we were in Europe using the 3 dB exchange rate, that constant would be approximately 10, not 16.61. So take our 16.61 and multiply it by our log result of 0.4393. That gives us approximately 7.271.
And the final step is to take that result and add our baseline, the 90. So 7.271 plus 90 equals a TWA of 97.271, or rounded to 97.3 dBA.
If we connect this to the bigger picture, it becomes very clear why we do this math.
Yeah, let's look at what we just proved. A chaotic, erratic workday consisting of 3 hours at 95 dB and 2 hours at a blistering 105 dB is acoustically, biologically, and legally identical to locking that worker in a room with a continuous, unbroken hum of 97.3 dBA for a full 8-hour shift.
Precisely. And now, armed with that TWA of 97.3 dBA, your mechanical engineer has actionable data. They know exactly how powerful the ambient sound field is, and they can start specing out acoustic baffles or noise-canceling enclosures rated to reduce a 97 decibel environment.
Let's run a second scenario to really cement how this formula handles different data, particularly data that indicates compliance. This one is pulled from the Yates reference guide.
Okay, let's hear it.
An industrial hygienist clips a small microphone, a dosimeter, onto a worker's collar at the beginning of their shift. The worker goes about their day, moving all over the facility. At the end of the shift, the hygienist checks the dosimeter, and it reads a total dose of 72%.
Immediately, we know the worker is legally compliant. They are under the 100% maximum budget. Their biological lawn is damaged, but it hasn't been completely crushed.
But again, I'm playing the role of the skeptical listener here. If the machine says 72%, and I know 100% is the limit, I know my worker is safe, why go through the administrative nightmare of doing this complex logarithmic math to find the decibel TWA? Shouldn't I just file the 72% report and go grab a coffee?
The larger implication here is proactive risk management and historical trend analysis. Yes, 72% is legally compliant today. But what if production speeds up next month? What if a machine ages and its bearings start to whine?
Ah, I see.
You need to know how close you are to the edge in absolute terms. Furthermore, OSHA regulations require specific interventions like mandatory hearing testing and training programs if the TWA hits the action level of 85 dBA, regardless of whether the dose is under 100%. You cannot confirm if you've hit that 85 dBA action level without doing the conversion.
Okay, that makes perfect sense from a regulatory standpoint. You have to know if you've crossed the invisible threshold where the paperwork begins. Let's run the 72% through the beast.
Let's do it.
Our dose D is 72. Divide 72 by 100, which gives us 0.72. Now we need the base 10 logarithm of 0.72. This is an interesting mathematical quirk because 0.72 is less than 1. Asking 10 to what power equals 0.72 forces the calculator to give us a negative number.
Yes, it will.
The log 10 of 0.72 is approximately negative 0.14.
We proceed with the formula exactly as before. We multiply that negative logarithm by our constant, 16.61. So 16.61 multiplied by negative 3.14 gives us negative 2.37.
And the final step is to add 90. But since our number is negative, we're essentially subtracting from the baseline. 90 plus a negative 2.37 results in 87.63 dBA, which we can round to roughly 88 dBA.
Right.
So a dose of 72% equals an 8-hour TWA of 88 dBA. They are under the 90 dBA permissible limit, but they are over the 85 dBA action level, meaning management still has to enroll that worker in a formal hearing conservation program.
Exactly. The math reveals obligations that the raw percentage might mask.
So we've established a solid foundation. We know how to measure the total biological impact on a single moving worker over a day, and we know how to translate that percentage into a decibel language that engineers can use to buy better equipment.
It's all connected.
But so far, we've only talked about the worker's relationship to the noise. Let's pivot and look at the environment itself. Let's imagine a factory floor. You don't just have one machine running. You might have 10, 20, or 50 machines running simultaneously.
That's a very common reality.
How do we calculate the baseline noise of the environment when multiple noise sources stack on top of each other? Because I know one thing for absolutely sure, based on the warnings in these source texts. You cannot simply add the decibels together like normal numbers.
No, you absolutely cannot. And it is arguably the most common and most dangerous intuitive mistake made by people newly entering the field of industrial hygiene.
Let me illustrate how absurd linear addition would be in acoustics. If I buy an industrial generator and the spec sheet says it runs at 80 decibels, it's loud but manageable. Then I decide I need more power, so I buy a second completely identical generator, place it right next to the first one, and turn them both on.
Okay.
If decibels were linear, like pounds or inches, 80 plus 80 would equal 160 decibels. To put that in perspective, a commercial jet engine at takeoff is around 140 decibels.
Right.
160 decibels is a concussive shock wave that would instantly rupture the eardrums of everyone in the room. Obviously, turning on two generators doesn't create a sonic weapon.
It doesn't, because decibels are a logarithmic expression of energy. When you add two sound pressure levels together, you are physically adding the raw acoustic energy, but then you have to recompress that new massive amount of energy back into the decibel scale. The Flieger Guide provides the precise scientific formula for doing this manually.
I am looking at the Flieger formula right now, and frankly, it looks like something designed to punish undergraduate engineering students. If you want to add 2 decibel levels scientifically, here's the 4-step process. Step 1, divide each individual decibel level by 10. Step 2, take the number 10 and raise it to the power of each result. This gives you the raw, massive acoustic energy numbers.
And then?
Step 3, add all of those giant raw numbers together. Step 4, take the base 10 logarithm of that massive sum and multiply the result by 10 to compress it back down into decibels. It is a grueling, multi-step process that practically demands a spreadsheet.
It is the only scientifically precise way to calculate complex acoustic environments. But realistically, if an inspector is standing on a loud factory floor wearing PPE and trying to make a rapid assessment of whether a new piece of equipment is going to push the room over the legal limit, they do not have the time or the clean environment to run 4-step logarithmic algebraic expansions.
Which is why the rule of thumb shortcut provided in the Bowen EHS guide is one of the most valuable tools in this entire curriculum. It is a field shortcut that allows you to estimate the combined noise of multiple machines incredibly accurately, entirely in your head.
The shortcut relies on calculating the simple numerical difference between the highest noise source and the secondary noise sources, and then adding a small fixed decibel penalty to the highest number.
Okay, let's lay out the rules of this shortcut. It operates on 4 simple brackets based on the difference between the volumes. Bracket 1. If the difference between the 2 noise sources is 0 or 1 decibel, you simply add 3 to the higher value.
Right.
Bracket 2. If the difference is between 2 and 4 decibels, you add 2 to the higher value. Bracket 3. If the difference is between 5 and 9 decibels, you add 1 to the higher value. Bracket 4. If the difference is 10 or more decibels, you add 0.
Those are the rules.
I want to push back on bracket 1 for a second to understand the why. Why do we add exactly 3 decibels if the difference is 0? Say I have 2 machines that are both exactly 85 decibels. The difference is 0. The rule says I add 3 to 85, giving me a total room noise of 88 decibels. Why 3? Where does that magic number come from?
It goes right back to the underlying physics we discussed earlier. When you turn on two identical machines, you are doubling the physical acoustic energy in the room, a 100% increase in raw power.
Okay, yeah.
And in the strict mathematical rules of the logarithmic decibel scale, a doubling of physical energy always translates to an exact increase of 3 decibels. The shortcut isn't magic. It is raw, foundational physics disguised as a cheat code.
That is brilliant. Okay, let's apply this cheat code to a practice problem from the Bowen EHS materials. We need to find the total volume of a room containing 3 distinct noise sources running simultaneously. A machine at 74 dB, a machine at 88 dB, and a machine at 75 dB.
The rule of the shortcut is that you must process them in pairs, always starting with the loudest sources.
So our loudest is 88, and our next loudest is 75. We find the difference between 88 and 75. The difference is 13. Looking at our shortcut brackets, if the difference is 10 or more, we add 0 to the higher value. So the combined noise of the 88 dB machine and the 75 dB machine is still just, well, it's just 88 dB.
The math proves it. And now we take that combined result of 88 dB and we pair it with our final machine, the 74 dB source. Again, the difference between 88 and 74 is 14.
And that is well over 10.
It is. Our rule tells us to add 0. So the final total combined noise of all 3 machines running at the same time is simply 88 dB.
That is wild to conceptualize. You have an 88 decibel piece of heavy machinery roaring away. You drag a 75 decibel machine and a 74 decibel machine right next to it, plug them in, turn them on, and the overall volume of the room does not change by a single measurable decibel. The 88 decibel machine completely and utterly dominates the environment.
It really does.
Let's look at a slightly more complex and very common real-world example from the Bowen text to really cement how this cascading calculation works. Imagine a large manufacturing floor. Workstation A currently sits at a steady ambient level of 89 dBA. Management decides production needs to increase, so they buy 3 brand new packaging machines and install them right next to Workstation A. The spec sheet for these new machines states that each one emits exactly 78 dBA.
Okay, so 3 new sources at 78 each.
What is the expected noise level at Workstation A after all 3 new machines are installed and turned on simultaneously?
We must combine them systematically, pair by pair, building the noise profile up. Let's start by combining the first 2 new packaging machines. Machine 1 at 78 dBA and Machine 2 at 78 dBA.
We look at the difference. The difference between 78 and 78 is 0, checking our shortcut rule. If the difference is 0 or 1, we add 3 to the higher value. 78 plus 3 gives us 81 dBA. So 2 78 dBA machines running side by side should create a combined total of 81 dBA.
Now we must add the 3rd new machine into that new combined total. We take our 81 dBA pair and combine it with machine 3, which is 78 dBA.
The difference between 81 and 78 is 3. We consult the rule. If the difference is between 2 and 4, we add 2 to the higher value. The higher value is 81. So 81 plus 2 equals 83 dBA. All right, so the block of 3 new machines generates a total combined noise footprint of 83 dBA.
For the final step, we must combine this new 83 dBA block of noise with the original existing ambient noise level of Workstation A, which was 89 dBA.
The difference between the 89 dBA room and the 83 dBA machinery block is 6. Our rule says if the difference is between 5 and 9, we add 1 to the higher value. The higher value is 89, so 89 plus 1 equals 90 dBA.
And there is your answer. The final total noise level of the entire floor is 90 dBA.
I really want to pause and emphasize the reality of what just happened. I brought 3 incredibly loud 78 decibel machines onto the floor. If you stood next to a 78 decibel machine, you would have to significantly raise your voice to be heard by someone standing next to you.
Oh, definitely.
I added 3 of those to a room that was already sitting at a dangerous 89 decibels, and the overall volume of the entire room only went up by a single solitary decibel, from 89 to 90.
It is deeply counterintuitive, but it perfectly illustrates the concept of acoustic dominance. When a highly powerful noise source exists in this case, the original 89 dBA environment, the acoustic energy of smaller sources is mathematically and physically swallowed up by the dominant sound pressure. Wow. Think of the 89 dBA environment as massive rolling ocean waves. The 78 dBA machines are just tiny ripples riding on top of those massive waves. They add a tiny bit of turbulence, but they do not change the fundamental height of the wave.
Let me frame this from a business and risk management perspective. Say you are a safety manager. An employee comes to your office and complains bitterly about a ventilation fan near their desk. They say the fan is driving them crazy. You measure the fan and it's putting out 75 decibels, but you measure the ambient noise of the entire production floor and the dominant machinery is roaring at 95 decibels.
Okay, a common situation.
If you spend $5,000 out of your safety budget to enclose that fan and silence it completely, turning its 75 decibels down to zero, what happens to the room?
Absolutely nothing. From a regulatory standpoint and from a dosimetric standpoint, protecting the worker's biological health, silencing that fan was a complete waste of resources.
Seriously?
Yes. The room will still measure exactly 95 decibels. The worker's dose will accumulate at the exact same terrifying rate. If you want to lower the TWA and actually protect the workforce, you must identify and target the dominant acoustic source. Small victories do not stack in acoustics.
Okay, so we've built the sound up. We know how multiple machines stack or fail to stack to create a dominant wall of sound. Now, let's talk about the most fundamental way to escape it. Because before we start engineering massive acoustic enclosures or handing out U-plugs, the simplest, most primitive defense mechanism humans have against noise is just, well, walking away.
The best defense.
How does physical distance impact this massive wave of acoustic energy?
Which leads us directly into the physics of wave propagation. Sound waves are raw physical energy moving through a medium, which in an industrial setting is typically the air. And as that energy expands outward from the machinery, it perfectly obeys the inverse square law.
The inverse square law. This is the principle that dictates that as you move away from a point source of noise, the sound pressure doesn't just decrease in a straight linear line, it drops off logarithmically as the energy is forced to spread over a larger and larger spherical area.
Exactly.
Here's where it gets really interesting. I like to use a visualization here to make the geometry less abstract. Think of a sound source like a grinding wheel as a can of spray paint.
Yeah.
If you hold the nozzle of the spray paint just 1 inch away from a brick wall and press the button, the paint, which represents the acoustic energy, is incredibly intense. It hits the wall in a thick, concentrated, highly dense circle.
Exactly. You have high total energy concentrated on a very small surface area.
But if you take 5 large steps back from the wall and press the nozzle for the exact same amount of time, the can releases the exact same volume of paint. The energy output of the source hasn't changed at all. But now that paint has to travel through the air, and as it travels, the cone of spray spreads out wider and wider.
Right, it diffuses.
By the time it hits the wall, that exact same amount of paint is spread over a massive surface area. The resulting layer on the wall is thin, misty, and weak.
That is a phenomenal analogy for the mechanism of the inverse square law. The total acoustic power generated by the machine's motor never changes. But as the pressure wave expands spherically outward in all directions, the acoustic intensity, which we measure as watts distributed over a specific square area, drops dramatically because the surface area of that expanding sphere is increasing exponentially.
And the source material gives us a specific distance formula to calculate exactly how much the sound drops over any given distance.
It does.
The formula is dB1 equals dB0 plus 20 multiplied by the base 10 logarithm of the ratio of the original distance, d0 divided by the new distance, d1.
Right.
The variables are pretty straightforward. dB0 is your starting volume. That 0 is the exact distance you were standing from the machine when you measured that starting volume. d1 is the new distance you want to move to, and dB1 is the final unknown noise level you were trying to calculate at that new location.
Let's test this mathematically with an illustrative example straight from the Bowen EHS question bank. We have an operator station located exactly 10 feet away from a massive industrial shaker. At that 10-foot mark, the safety inspector's decibel meter registers the sound level at a dangerous 103.0 dB.
That's really loud.
It is. The facility manager wants to know if we physically relocate the operator's control station to a spot 45 feet away from the shaker, what will the new estimated sound level be?
All right, let's plug the reality into the math. Our starting volume dB0 is 103.00. Our starting distance d0 is 10 feet. Our new distance d1 is 45 feet. First step, we divide the original distance by the new distance. 10 divided by 45 gives us a ratio of 0.222.
Next step, we take the base 10 log of 0.222. Just like before, because it's a fraction less than 1, the logarithm is going to be a negative number. The log 10 of 0.222 is roughly negative 0.65.
Then, following the formula, we multiply that logarithm by the constant 20. So 20 times negative 0.65 equals exactly negative 13.1. Final step. We add that result to our original noise level. 103.0 plus a negative 13.1, which is simply 103 minus 13.1, gives us 89.9 dBd.
The result is staggering when you consider the biological implications. By simply unbolting the operator's chair and moving it from 10 feet to 45 feet away, you drop the noise exposure from a highly hazardous wire under 3 dB down to 89.9 dB.
Which changes everything. 103 dB means the worker can legally only be there for less than 1.5 hours before they exceed their daily dose, and the employer faces massive liability. But 89.9 dB is technically under the 90 dB OSHA permissible limit. By moving them 35 feet, you've transformed a task that required extreme administrative oversight and heavy PTE into a task they could potentially perform for a full 8-hour shift.
It demonstrates the profound power of distance as a primary engineering control. It is often the cheapest and most effective way to eliminate a hazard. And the physics of this law aren't restricted to heavy industrial equipment. The Waze mechanics apply to any point source of sound.
Which brings us to my absolute favorite practice question in the entire Bowen guide. It's designed to prove that this formula is universal. It's called the Irishman question. When you first read it, it genuinely sounds like the setup to a pub joke.
It really does.
The problem states, an Irishman generates a certain amount of noise at 20 paces. How much noise is he generating at 12 paces? And the multiple choice answers actually include Irishman, Englishman, and neither. But it isn't a joke. It's a pure physics problem.
It mathematically proves that human vocal cords follow the exact same physical laws of acoustic expansion as a diesel generator. If you plug his initial volume at 20 paces into the dB0 slot and 20 into the DO0 slot, you can calculate his exact volume as he approaches you at 12 paces.
The origin of the sound is completely irrelevant to the behavior of the pressure wave. Once the acoustic energy leaves the source, it is bound by the geometry of the expanding sphere.
Exactly.
And industrial hygienists use this spray paint formula, this expanding sphere geometry, to do something incredible on the factory floor. They use it to paint invisible architectural boundaries. They can literally take a piece of chalk, run this distance formula in reverse to find the exact footage where a 105 dB machine drops below the 90 dB bath threshold and draw a bright yellow line on the concrete. They mandate that if you cross this line, hearing protection becomes legally mandatory.
They are charting the geography of the hazard, turning an invisible threat into a map zone.
But I want to introduce a harsh reality check. All of this math, the inverse square law, the spray paint analogy, it all assumes that the sound wave can expand outward freely. It assumes you are in an open field or an impossibly massive warehouse. What happens when the geography works against you?
That's where things get complicated.
What if the noise is trapped in a small enclosed room with you? Or what if the operator's job physically requires them to stand 2 feet away from the grinder to manipulate the controls? You can't rely on the inverse square law if you physically cannot increase the distance.
When increasing distance is physically or operationally impossible, we can no longer rely on the air to dilute the sound. We have to look at modifying the physical environment itself and ultimately modifying the worker's interface with that environment.
So if we hit a wall, literally we need to understand what the wall is doing to the sound. If you fire an acoustic wave into an enclosed room, it doesn't just travel from the machine straight into the worker's ear. It hits the drywall, it hits the ceiling, it hits the concrete floor, and it bounces back. It creates a chaotic web of reflections.
We call that reverberation. The initial noise from the machine is the direct field, and the chaotic bouncing noise is the reverberant field. And not all building materials handle those impacts the same way. The Flieger Guide provides a deep dive into the acoustic properties of industrial building materials, defining what is known as the absorption coefficient.
Let's unpack the absorption coefficient. It is essentially a metric of how much acoustic energy a specific material swallows up and converts into microscopic heat rather than reflecting it back into the room as noise. The scale is very simple. It goes from 0 to 1. A coefficient of 0 means the material is a perfect acoustic mirror. It bounces 100% of the sound back. A coefficient of 1 means it is a perfect acoustic black hole. It absorbs 100% of the energy.
And crucially, a material's ability to absorb sound is not static. It varies drastically depending on the frequency or the pitch of the sound wave striking it, which we measure in hertz. A material might easily absorb high-pitched screeches, but completely fail to absorb low, rumbling bass frequencies.
The data tables in the Flieger Guide are a revelation for anyone interested in architecture. Let's look at how common building materials perform at 1,000 hertz, which is a mid-range frequency, right in the critical sweet spot of human speech and general mechanical noise. At 1,000 hertz, poured concrete has an absorption coefficient of 0.02. That is abysmal.
It really is.
It means it is absorbing only 2% of the energy and bouncing 98% of the noise straight back at you. Standard brick is slightly better at 0.03. Heavy wood paneling gets up to 0.07. Plywood hits 0.1, but then you look at carpet. Standard, heavy carpet laid on a floor at 1,000 hertz has a massive absorption coefficient of 0.37.
It is actively stripping 37% of the acoustic energy out of every wave that strikes it.
Let me paint a picture of why this architectural data is life or death for hearing conservation. Imagine you take a roaring 100 decibel air compressor and lock it in a small, unfinished basement made entirely of pure concrete walls and a concrete floor.
It's awful.
It is. The sound waves blast out, hit the concrete, and bounce back almost completely intact. They cross over each other, creating standing waves and amplifying the acoustic chaos. The reverberant field actually makes the room louder than the machine itself. It is a terrifying acoustic nightmare.
Truly.
Now imagine taking that exact same 100 decibel compressor and placing it in a cozy, fully carpeted living room with heavy drapery and plush furniture. The carpet and the fabric act like sonic sponges. Every time the wave hits a surface, a huge percentage of the energy is swallowed. The environment itself acts as an active dampener, starving the reverberant field.
This architectural reality is why engineering controls so often involve retrofitting existing industrial spaces. Facility managers will install suspended acoustic baffles from the ceiling, line the walls with specialized dampening panels, or apply absorbent foams that are chemically engineered to target the specific frequency spectrum emitted by the dominant machinery. You force the environment to fight the hazard for you.
But let's be pragmatic. Sometimes, even after you've applied the distance rules, and even after you've lined the walls with acoustic foam, you simply cannot get the total volume below the 90 dBA PEL. Or even if you do get it under 90, you can't get it below the 85 dBA action level, where proactive medical surveillance becomes mandatory.
That happens all the time.
When the environment cannot be fully tamed, OSHA mandates the implementation of a comprehensive hearing conservation program, or an HCP. The texts outline 5 specific, non-negotiable pillars of a robust HCP.
Yes, these 5 pillars form the administrative safety net. Pillar 1 is exposure evaluation. This is everything we've spent the bulk of our time discussing today. It is the active monitoring of the facility, strapping dosimeters to workers, calculating their doses, and translating those into TWAs, so management knows exactly who is at risk. You cannot fix what you do not measure.
Right.
Pillar 2 is engineering control. This is the implementation of the distance boundaries, the acoustic enclosures, and the absorbent materials we just analyzed. It is the attempt to physically remove the hazard from the air. Pillar 3 is audiometric testing. And this is the biological reality check. This is where you test a worker's hearing on the day they are hired to establish a baseline, and then you mandate annual hearing tests. The medical professionals are looking for what is called a standard threshold shift, or an STS. An STS is biological proof that your worker is losing their hearing. It is the grim confirmation that your controls, your baffles, and your distance lines are actively failing.
Exactly. Pillar 4 is training. It is legally required that workers understand the invisible hazard. They need to understand the physics of why that loud machine is permanently crushing their stereocilia and why they must participate in the program.
And Pillar 5 is record keeping. The endless documentation of every dosimeter reading, every audiogram, and every training session, ensuring there is a paper trail of compliance and health tracking over the worker's entire career.
And nestled within this program, only to be utilized when the engineering controls have been entirely exhausted and the air remains hazardous, we reach the final ultimate mitigation strategy: personal protective equipment, hearing protectors, earplugs, and earmuffs. Which brings us to a concept heavily featured in the Bowen CSP exam questions: the NRR. The NRR stands for the noise reduction rating. It is that bold number you see printed on the side of every single box of foam earplugs at the hardware store. Conceptually, it tells you how many decibels of noise the protective equipment is capable of blocking from reaching your eardrum.
Right.
So simple math would suggest if you are forced to work in a room dominated by 100 decibels of noise and you insert earplugs with an NRR of 30, you subtract 30 from 100 and assume your eardrum is only experiencing a safe, compliant 70 decibels.
That is the theoretical laboratory math. However, the reality of occupational safety requires a much more cynical approach. Industrial hygienists must severely deprate the printed NRR because laboratory testing does not reflect human behavior.
Why is that?
Well, in a lab, a scientist perfectly rolls the foam earplug, inserts it deeply into the ear canal, and holds it there while the foam perfectly expands to create an airtight seal.
But on a factory floor at 6 a.m., a worker with dirty gloves takes the earplug, barely squishes it, jams it halfway into their ear, and lets it hang out like a cigarette. Or they wear safety glasses with thick frames that break the airtight seal of their earmuffs.
Exactly. Because human application is so flawed, OSHA actually recommends a D-rating formula for field use. You take the printed NRR, subtract 7, and then divide the remainder by 2, so that NRR 30 earplug. 30 minus 7 is 23. Divided by 2 is 11.5. In the real world, you can only mathematically trust that NRR 30 earplug to block about 11.5 decibels of noise.
Wow, that's a massive drop. I want to use that D-rating reality to challenge the fundamental philosophy of safety programs. If I'm a factory owner, why am I forced to spend tens of thousands of dollars on complex engineering controls? Why do I have to buy expensive acoustic baffles or redesign my floor plan to increase distance? Why can't I just buy a massive pallet of NRR 30 earplugs, hand them out on day one, and say, wear these, you're safe? Why is PPE considered the absolute last resort in the hearing conservation program?
This raises an important question, and it comes down to the hierarchy of controls, which is the foundational philosophy of all risk management. You rely on engineering controls because they alter the physical reality of the environment, independently of human behavior.
Right.
An acoustic baffle hanging from the ceiling works 24 hours a day, 7 days a week. It cannot be forgotten in a locker. It does not pull itself off the wall to hear a coworker tell a joke. It provides absolute passive protection.
But PPE is entirely reliant on the worker acting perfectly.
Precisely. If an earplug is inserted improperly, or if the worker pulls it out for just 5 minutes in a 105 decibel environment to communicate, the protection level instantly drops to 0. The worker is immediately subjected to the full, unmitigated violence of the acoustic hazard. We must engineer the hazard away from the environment whenever physically possible and rely on the NRR only to bridge the final, unavoidable gap.
So let's step back and survey the landscape we've just mapped out. We've taken a massive journey through the invisible world of acoustic hazards. We started by dissecting the strict regulations of OSHA, exploring the tension between NIHL's pure 3 dB physics and OSHA's 5 dB exchange rate, the regulatory compromise that forces you to have your working time for every 5 decibels, the volume increases.
It's a lot to process, but it's essential.
It is. We took that rigid rule and applied it to the chaotic reality of a worker's shift, calculating their personal daily dose by dividing the time they actually spent in the noise by the time they were legally allowed to spend, summing up a percentage that represents the biological stress placed on their inner ear.
The stomped grass.
Exactly, the stomped grass.
Yeah.
But because mechanical engineers can't buy equipment to fix a percentage, we explored the logarithmic formula required to convert that biological dose back into a time-weighted average, TWA, translating human damage back into the decibel language of facility design.
We covered a lot of math today.
We did. We unraveled the counterintuitive physics of adding multiple machines together, utilizing the +3 decibel rule of thumb to prove that because acoustic energy is logarithmic, a dominant loud machine will completely swallow the noise of smaller machines, forcing management to stop wasting money on minor annoyances and target the true hazard.
Which is such an important takeaway for safety managers.
Then we mapped the physical geography of the hazard, using the inverse square law to prove that moving away from a source exponentially drops the acoustic intensity as the energy is forced to stretch over an ever-expanding spherical area. And finally, when distance wasn't an option, we looked at how the architectural materials of the room itself, the absorption coefficients of carpets versus concrete, dictate the danger of the reverberant field, and how the 5 pillars of the hearing conservation program serve as our final, heavily managed safety net.
It is a remarkable progression from theoretical physics and logarithmic algebra right down to the practical reality of rolling a piece of foam between your fingers. It proves that occupational safety is not arbitrary rulemaking. It is rigid physics, acoustics, and mathematics meticulously applied to preserve human well-being.
And as we wrap up this deep dive into the source material, I want to leave you, the listener, with a final thought to mull over, something to carry with you that builds on everything we've unpacked today. I want you to think about the invisible architecture of sound that surrounds you right now and every single day. Every room you enter, every street corner you cross, every restaurant you sit in is the physical manifestation of acoustic math interacting with building materials.
It really changes how you look at the world.
It does. The next time you walk into a cafe and find it beautifully peaceful, or conversely, you walk into a crowded bar and find it totally overwhelming, realize that it isn't magic, and it isn't just the volume of the people. Your brain is instantaneously performing the exact logarithmic calculations that we spent the last hour discussing. Your ears are measuring the inverse square drops from the speakers. They are processing the absorption coefficients of the exposed brick walls versus the padded seating. They're intuitively computing the combined decibel dominance of the espresso machine over the background music.
That's a great way to put it.
You don't need a certified dosimeter clipped to your collar to understand the physics of your environment. You are a walking, breathing dosimeter. You just have to learn how to read the data your body is already collecting. Thank you so much for joining us for this edition of QHSE Talks. Keep listening, keep questioning the numbers, and stay safe.